Today we are going to learn about mastering TensorFlow checkpoints for model recovery. In this session, we'll explore how to effectively use TensorFlow checkpoints to save and recover model states, enhancing training efficiency and minimizing data loss.
Hello and welcome. In this session, we will dive deep into the world of TensorFlow checkpoints, a critical feature for anyone working with machine learning models. Checkpoints are essential for saving the state of your model during training, which helps prevent data loss and allows you to resume training seamlessly in case of interruptions. Throughout this video, we'll explore how checkpoints can enhance the robustness of your models and make your training processes more efficient. Let's get started on this journey to mastering TensorFlow checkpoints for model recovery. In the world of TensorFlow, understanding the distinction between checkpoints and saved models is crucial. While checkpoints are snapshots of your model's state at a particular point, enabling you to resume training, saved models are comprehensive exports of your model that include the architecture, weights, and optimizer states. Checkpoints are primarily used during the training phase, allowing for efficient recovery and continuation. On the other hand, saved models are designed for deployment and inference, encapsulating everything needed to run the model outside the training environment. Knowing when to use each can significantly impact your workflow and model management strategy.
To effectively use checkpoints in TensorFlow, we need to integrate them into our training process using callbacks. The ModelCheckpoint class in TensorFlow Keras API allows us to automate the creation of checkpoints during model training. By specifying parameters like file path, save_best_only, and monitor, we can customize how and when checkpoints are saved. This setup ensures that our training process is resilient to interruptions, as we can always resume from the last saved state. Incorporating these callbacks into our training loops not only enhances fault tolerance but also boosts training efficiency by minimizing redundant computations. Determining how often to save checkpoints is a critical decision in the training process. Configuring the frequency of checkpoints involves balancing the need for up-to-date model states with storage limitations. In TensorFlow, this can be done by setting parameters like period or save_freq in the ModelCheckpoint callback. Additionally, adopting clear naming conventions for checkpoints, such as including epoch numbers or validation metrics in file names, can facilitate easy identification and management of checkpoint files. Organizing these files into structured directories ensures that your training process remains efficient and manageable, even with frequent checkpointing.
One of the primary advantages of checkpoints is the ability to restore models and resume training with minimal disruption. To achieve this, TensorFlow provides straightforward methods to load checkpoint data back into your model. By using the tf.train.checkpoint class or the Keras model's load_weights method, you can easily rehydrate your model with the saved weights and states. This capability is invaluable in long training sessions, where unexpected interruptions can otherwise mean significant losses in computational time and resources. Ensuring the integrity of your checkpoints and verifying their successful loading is key to maintaining the continuity of your training process. Despite our best efforts, there are times when checkpoints might become incomplete or corrupted due to various factors such as disk failures or abrupt terminations. Identifying these issues early can save a lot of headache. TensorFlow provides tools to check the validity of checkpoint files before attempting to use them. Implementing robust error handling mechanisms in your code can help detect and manage corrupted checkpoints, allowing your training process to recover gracefully. Additionally, taking preventive measures like using reliable storage solutions and regularly validating your checkpoints can significantly reduce the risk of corruption and ensure the integrity of your data. As model training processes become more complex and data-heavy, leveraging cloud storage solutions for managing checkpoints becomes increasingly beneficial. By integrating TensorFlow checkpoints with platforms like Google Cloud Storage, GCS, you can ensure that your model states are securely backed up and easily accessible from anywhere. TensorFlow provides built-in support for cloud integration, allowing you to configure checkpoints to automatically synchronize with your cloud storage. This setup not only enhances data security but also offers scalability and accessibility advantages, making it a preferred choice for many practitioners working with large-scale models and datasets. Effective management of checkpoint files is crucial to maintaining a smooth and efficient model training process. Organizing your checkpoint files into well-structured directories can help you keep track of different versions and states. Regularly cleaning up outdated or unnecessary checkpoints helps optimize storage usage and prevents clutter. Monitoring your storage utilization allows you to anticipate and mitigate potential issues related to disk space. Implementing version control systems for your checkpoints can add an additional layer of security and traceability. Automating these management tasks through scripts or tools can significantly ease the burden and improve the overall efficiency of your training pipeline. When working with large-scale models, traditional checkpointing strategies might not suffice due to the sheer size and complexity of the data involved. Advanced techniques such as distributed training and checkpoint partitioning can help manage these challenges effectively. By distributing model training across multiple nodes, you can save checkpoints more efficiently and reduce the load on individual systems. Optimizing the performance of checkpoints involves balancing the size of the files with the level of detail they contain, ensuring that you capture all necessary information without overwhelming your storage resources. Strategies like these enable you to handle large datasets efficiently, maintaining the robustness and reliability of your training processes.
Despite the robustness of TensorFlow checkpoints, users often encounter common issues that can disrupt training processes. Errors related to loading checkpoints, version compatibility, and inconsistent training resumes are among the most frequent. Debugging these issues requires a systematic approach, starting with verifying file paths and ensuring compatibility between checkpoint versions and TensorFlow updates. Consistently documenting your workflow can prevent many common pitfalls associated with checkpointing. Understanding these troubleshooting techniques will equip you with the skills to quickly resolve any checkpoint-related issues, ensuring your model training remains smooth and efficient.
With the release of TensorFlow 2.x, several enhancements have been introduced to simplify and improve the checkpointing process. The API has been streamlined, making it more intuitive to use and better integrated with the Keras framework. These changes have led to improved performance and usability, making the process of saving and recovering model states more efficient. New features have been added to support model recovery, offering users more flexibility and control over their training processes. Understanding these updates and how to leverage them will help you stay at the forefront of TensorFlow development, ensuring that your models are as robust and efficient as possible. As we wrap up this session on mastering TensorFlow checkpoints for model recovery, let's recap the key concepts we've covered. We explored the importance of checkpoints in preserving model states and enhancing training robustness, discussed the differences between checkpoints and saved models, and examined best practices for managing checkpoint files. By applying the skills and strategies discussed, you'll be well equipped to handle long training sessions and minimize data loss. We encourage you to apply these techniques in your projects and explore further resources to deepen your understanding of TensorFlow checkpointing.